What's going on, everybody? It's High Peak Education coming back at you with another physics video. And this time an example problem having to do with rolling motion. Rolling without slipping and conservation of energy. So let's take a look at this problem. It says that a cylindrical hoop, a solid cylinder, which we know as a disc, and a solid ball are placed at the top of an incline of height 2.00 meters. They are simultaneously allowed to roll to the bottom of the incline. A. Calculate the velocity of each object when they reach the bottom of the incline. B. Calculate the velocity of any objects that slide to the bottom without rolling in the absence of friction. Okay, so let's do each of these separately. Let's do the hoop in red. Let's kind of sketch what it looks like. And then let's sketch a disc in blue and a solid ball in green. Okay, so a hoop I think is going to look like so. Something like this. Okay, where pretty much all the mass is on the outside. Okay, now by the way, these are all going to roll down an incline. You may wonder what the angle of that incline is. And it turns out, as we'll see, it's actually not going to matter. But we do know this incline has a height that's given. And that's given at about 2.0 meters. So that's this distance here, and that's h. Okay, so there's our hoop. So all the mass on the outside. Here's the formula for the rotational inertia. Let's do the same sort of thing for the disc. So let's put the disc here next to this hoop. It's going to start at about the same height. Now you may wonder, what if the disc has a different radius than the ball? It turns out that, interestingly enough, that's not going to matter either, and we'll see why that is. I'll prove that to you in this problem. Okay, and then finally a solid ball. So this is a sphere, and this I'll just sketch. So the solid ball is going to be something like this, and the idea is that it's a sphere, and so there's mass everywhere on the inside. Okay, but again, it's a solid ball. So this right here is a sphere. It's hard to sketch, but you get the idea, hopefully. And again, you may wonder about its radius. But as it turns out, believe it or not, it's actually not going to matter. So let's see if we can work these out. Okay, so it turns out that for rolling motion, we can model these in terms of the conservation of energy. So we're going to assume that there is no slipping. So with there's no slipping, we're going to assume that each of these objects touch at one exact point on the incline, so that there is static friction. But we're going to assume no rolling or kinetic friction, so to say. Furthermore, we're going to assume no air resistance or no non-conservative forces. And again, the height of this thing is going to be 2 meters. Okay, you could assume there's a 90-degree angle, but you hopefully just get the idea. All right, so they're simultaneously allowed to roll to the bottom of the incline. So we can use the conservation of energy. In fact, the conservation of mechanical energy should say the following: that the initial gravitational potential energy, so this is UG initial, is equal to, at the bottom here, the final rolling kinetic energy. Now, what is rolling kinetic energy? Well, it's made up of both the linear and the rotational kinetic energy. That is, it's translational plus spinning kinetic energy. So the initial gravitational potential energy in this case would be like capital M, G, H. H here, you can imagine, is the initial height. Okay, let's assume the final height right here, by the way, this is H equals 0 meters. Okay, so we could put an HI for an H initial on there, that's fine. Okay, how about the rolling kinetic energy? That's, again, the translational plus the rolling kinetic energy, plus the rotational kinetic energy. So again, this right here is linear, and then this right here is due to the spin. So believe it or not, when something rolls, it actually translates its center of mass and it spins its center of mass simultaneously. And that's what it means to roll. So the translational kinetic energy is the traditional 1/2 mv squared. Now let's put v final because we wanted the final velocity down here. And then the final rotational kinetic energy would be 1/2 I omega final squared. Okay? Now let's think about how this is going to work. Oh, and by the way, just so everything coordinates, let's have this mass here be the mass of this big M, the same as the big M's in here. So it's the mass of each shape. So just for agreement, let's make this big M. Okay, so all looks good. That's the mass. All right, so going on from there, let's see how this problem's going to work out. Notice that I is going to be the rotational inertia. It's going to be the rotational inertia of each shape, namely red, blue, and green, namely hoop, disc, and solid ball, namely mr squared, 1/2 mr squared, or 2/5 mr squared. So we can deal with each of these sort of in turn, one at a time, for each of these i's. So this will go in here depending upon the shape. Okay, so we'll get to that in a second. Also, since we're interested in how fast it's going horizontally, that is the center of mass, we'd be interested in getting omega final in terms of the linear velocity. So omega final, I think, should be the final linear velocity divided by the radius. And notice that that just comes from the rotational and linear relationships. So this can be substituted into here. Okay, so in fact, let's do that for these shapes. Okay, so let's start off with the hoop first. So for the hoop first, notice that you'll have the equation mgh initial is equal to, let's see, 1/2 m v final squared plus 1/2, and then in for I goes mr squared, and then in for omega final goes v final squared over r squared. Now here's the amazing thing. Notice that in this conservation of energy equation, the masses cancel. Notice this is not too uncommon from other conservation of energy equations. It's independent of mass. Independent means it doesn't really matter what the mass is. Doesn't really matter in some sense, almost like even what the density of these things are, because if you have more mass, sure, you have more potential energy, but it's also harder to build up kinetic energy. So the net effect goes away, the mass cancels. Now here's something else that's quite interesting. Look at these radii. See how there's an r squared here and an r squared below? Those also cancel. So that's kind of interesting. Notice that it's independent of mass and independent of radius. And let's think about why that could be the case. You may think that a large hoop, in other words, a large radius, gives you a larger linear velocity, right? Because you could think from omega times r gives v, and then that gives a larger tangential velocity. You might think bigger wheels or bigger hoops give you a larger linear velocity. But wait, there's more. There's actually less linear velocity because look at the rotational inertia. If the radius is greater, the rotational inertia is greater. Even though something should have a larger linear velocity, it's also harder to get it rotating. So the net effect of those two cancels. So here we'll just have 1/2 v final squared. Now notice 1/2 v final squared plus 1/2 v final squared, I think we'll just have literally v final squared equals gh initial. This is gh initial equals v final squared. Okay, so there we go. And notice that we just need to take the square root of this to get the final velocity. Okay, so this is going to be square root of gh initial equals v final. And this we can calculate from the square root of 9.8 meters per second squared times h initial of 2.00 meters. Now we'll calculate that in just a moment, because I want to compare that to the hoop as well as the disc and the solid ball. So now let's take a look at the disc. So notice the disc is going to be the exact same equation, mgh initial equals 1/2 mv final squared plus 1/2. But notice the rotational inertia term will be different. It'll just be 1/2 mr squared times v final squared over r squared. Notice it works out exactly the same, that the masses cancel and these radii cancel, but now we have 1/2 v final plus 1/4 v final squared. These are v final squareds. So I think that's a half plus a fourth, which is 3/4. So I think that we get gh initial is 3/4 v final squared, which works itself out to 4/3 gh initial, and the square root is v final. So this is going to be 4/3 times 9.8 meters per second squared times 2.00 meters, and the square root of this number. Okay, so we'll get that number in a second as well. And then finally, I know you're on the edge of your seat, but what about the solid ball? Well, the solid ball should be like the following. mgh initial equals 1/2 m v final squared plus 1/2, this times 2/5 mr squared. Only the rotational inertia is different. In fact, the rotational inertia is less, so just like here we got a larger final velocity than the hoop, we should get an even larger final velocity for the solid sphere, which is the ball. Again, the radii cancel and the masses cancel, just as before, but this time I think we have 1/2 times 2/5, which is 1/5. So 1/5 plus 2/5, 1/2, 1/5 plus 1/2 is, I think, 2/10 plus 5/10. So I think that's 7/10. So we get gh initial is equal to 7/10 v final squared. So this is 10/7 gh initial, and the square root is v final. And again, that's going to be 10/7 times 9.8 meters per second, to meters per second squared, times 2 meters, and the square root of this. Okay, just about ran out of room. So let me go ahead and see if I can calculate these. So for the first one, I think we have the second square root of 9.8 times 2. That's the hoop. 4.42 meters per second. So about 4.42 meters per second. Okay, there we are. Then let's do the same thing for the disk, but with the disk we have to multiply by 4/3 under the square root. So we'll repeat this calculation, but we'll go back here, we'll do second insert, and we'll go parentheses 4 divided by 3, close parentheses, and a multiply. So we should have our correct expression. So that's 5.11 meters per second. So about 5.11 meters per second. And I'm about out of room, so I'll squeeze the solid ball up here in green. So repeating the last calculation, but instead of 4/3, making this 10/7. Again, let's do second insert mode. 10. Let's mouse over to just delete and then make this a 7. So 10/7 times 9.8 times 2. Notice that we've got 5.29 meters per second. Okay, let's write that down. So this up here is about 5.29 meters. Okay, so notice what's going to happen here. After these things roll along, especially after they're moving some constant velocity, say on the ground, the sphere is first, followed closely by the disk, and then after that by the hoop. Okay, so sphere followed closely by the disk, and then quite a bit later by the hoop. Okay, so it should be in this order. This should be the order that who wins the race. Let's say they're all released at the same time. So notice, why does the sphere win? The sphere has the smallest rotational inertia, the smallest moment of inertia. So it requires the least rotational kinetic energy. So it can receive the greatest linear kinetic energy. Since the linear kinetic energy is greatest for the sphere, it ends up with the largest linear velocity, that is the largest translational kinetic energy, for its center of mass. So the sphere is moving fastest at the bottom of the incline. Whereas the cylinder is moving not as fast, but still pretty fast, 5.11 meters per second. And then the hoop is moving the slowest because all of its mass is on the outside. That's just mr squared. And so notice it's going to basically be moving the slowest. Okay? Now, by the way, notice that if it was reversed, if these are going to, let's say, go up a hill, and they're all going to go up a hill, and they're all going to have different, if they're all going to have the same translational velocity, I think the hoop will actually reach the highest. And we can see that in the next example problem. By the way, we want to do this calculation if the objects slide to the bottom without rolling in the absence of friction. Now in that case, that's part B. That one's pretty straightforward because for part B, it should only be the gravitational potential energy is equal to the final linear kinetic energy. And that's going to be mgh initial equals 1/2 mv final squared. We can just cancel out these masses. This is 2gh initial, and the square root is v final. So let's perform this calculation. So notice this will just be square root of 2 times that of the hoop, okay? And 2 is larger than 10 over 7, even so. So 14 over 7 would be a factor of 2. So that'll be fastest. Because if these objects just slide down without friction, it won't require any rotating, and so it'll actually go fastest if they just slide down without any rolling. So all the energy is going to go into just translation of the center of mass. So if we second insert and we do 2 times 9.8 times 2, we should have 6.26 or so. So about 6.26 meters per second. And this right in here is just part B. So notice that, again, if you don't have any need for rotating kinetic energy, all the kinetic energy can move the center of mass, and any object would slide down faster than it rolls. Okay, so that ends this problem. Thank you very much for your attention. Please smash that like button if you enjoyed this content. Please subscribe to the channel to grow the channel. Please share this amongst your social network. Please also comment on the video if you like, and I look forward to reading your comments. I will see you in the next video. Thank you for watching High Peak Education.